Hi, I'm Sophia, and this is my week 11 reading. Week 12. So this week we extended the idea from last week about time changing magnetic fields inducing an EMF in a wire. So last week we talked about how external magnetic fields can, produced by another source, can induce an EMF in a wire and kind of create an induced current. But this week we talked about how if you plug in a wire into a battery and you're going to get an increase in current, this increase in current can induce a magnetic field within the wire itself, and this magnetic field can then induce an EMF in the same wire that created the magnetic field. This is called self-inductance. And so we discussed self-inductance in the context of solenoids. So we had hooked up a solenoid to a battery and then observed an increase in current flow in the solenoid and then a magnetic field that generates an EMF in the solenoid. And so changes in magnetic flux through the solenoid induce an EMF. And so we derived an equation for EMF that includes the change in current flow and the inductance, and we obtained the inductance from rearranging some terms in the equation. And so we also discussed how by the loop rule, the EMF induced in the solenoid by the change in current is going to be equal to the EMF of the battery, and it's going to be opposite in magnitude. That's because, by the loop rule, the changes in EMF across the circuit have to basically equal to 0. Okay, so then in the following video, we talked a little more about inductance and resistance. So we rearranged that equation that we derived for the EMF that included change in current over time and the inductance. And so we rearranged it to solve for the change in current over time. And that equation involved something called the time constant, which is the inductance divided by the resistance. So the time constant is the time it takes for the current to increase significantly from 0 when the solenoid has just been hooked up to the battery. So to increase from 0 to a value that's close to steady state. In fact, this value is within a factor of 1 minus e to the negative 1 of the steady state current flow. And so finally we concluded with talking about Gauss's law and electric flux over a closed surface. So we talked about how we would integrate the dot product of the E field and the area vector over the surface to get the change in electric flux. And so the area vector points in a direction perpendicular to the surface, and its magnitude is equal to the area of the surface. And so the change in flux also happens to be the enclosed charge divided by epsilon naught. And so some things that were familiar from previous weeks were the loop rule, when we were talking about how the EMF from the induced current, or the induced EMF from the current flowing through the solenoid is equal and opposite to the EMF of the battery. And that's because the round-trip change in electrical potential across the circuit has to be 0. So this is kind of an extension from last week's concepts. And something that I didn't know was inductance and exactly what that represents. And I guess I'm still not very clear on the conceptual understanding of inductance. I guess I understand how it's used to calculate the time constant, and I understand what the time constant tells us, but I don't conceptually understand what inductance does. And I guess that's my most difficult physics idea for this week. So I'll have to research that a little more and, ask on Campus Wire also if I can't find the necessary information. And, so something that I found particularly interesting this week is that the whole idea of current flowing through a wire inducing an EMF in the same wire or solenoid or whatever it's flowing through. I guess we never studied EMFs in this context, and it was just interesting to think about it this way. It doesn't really relate to my field of study too much, but it was still interesting. Yeah, all right. Thank you guys for watching.